Hi and hello everyone. What we are seeing now are the queuing systems that can be modeled by a general continuous time Markov chain, or what we generically call as Markovian queuing models, general Markovian queuing models, meaning non-birth death queuing models, in which the first group, so we are still within in some sense Poisson exponential assumptions, and in which we just considered what we called it as a bulk arrival queue, and we saw how it can be analyzed. What we will see next is that what we call it as a bulk service queuing models. Okay. So, this bulk service models is similar to that in the notation wise what we are using it is M, and M the superscript y/1 is what is the model that we are going to look at it. We are looking at single server models only. Okay. So, what we have, we are considering a single server Markovian queue with bulk service. So, what are the typical examples? So, the mass transit vehicles or mass transit carriers are very good natural examples which serves the customers, what we call the customers in batches, right. So, this is natural batch servers. So, all the assumptions that we have made with respect to MM1 are applicable here. If you look at here, what we have is that the arrivals follow a simple Poisson process, right. Service times are distributed as exponential, and there is a single server, and whatever the assumptions that we have assumed. And also additionally, what we assume that the customers are served in groups or batches of size k, and it is a specific thing that we are looking at it, okay, of size k. Now, this batch size is we are keeping it as independent of the any other thing that we are considering within the model. So, that is what is the batch size. So, here the notation wise we just kept it y, which could be any random variable, but the consideration that we are making it is batch size k. Now, within this structure there we are considering two variations based on how the system behaves when there are less than k customers in the system. When there are less than k customers in the system, how the system behaves. Based upon that, we could have what we call it as either full batch model or partial batch model. Now, what is a full batch model? So, here the server processes exactly k customers at a time, and if less than k customers are there in the system, then the server remains idle until there are k customers in the system, at which point the server starts the process of this k customers simultaneously. The service times are exponential with parameter mu for the whole batch. So, and hence it is the same for all customers in the batch. So, it is for the whole batch the service time is exponential with parameter mu. For example, you can think of it an example, a small ferry service that crosses the river only when it is full. Say for example, if you look at it in some places, there are small ferries which only when it is full it will cross the river or go to certain island and so on, right. It may not be the case that they are working on some time scheduled manner, right. It might be, if that is the case, then it is a slightly different model. But there are some private ferry services that might cross the river only if, say if they have 10%, they can hold only up to 10, finish, right. So, I am just giving a simple example, but there could be many different situations which you can think as if it can happen in this way, right. In a production system or in anywhere, like this can easily be taken into account because of this cost effective manner, like you will have only when there are k items are there, you start the processing of that all together, because all of them would take the same time, right. So, that is the possible idea which we have full batch, meaning there are k is a fixed number here, and the server always processes k customers at once following an exponential distributed service time. Now, as opposed to this full batch model, there could be another variation of this model, which is partial batch model, right. So, here, and in fact, this is what is the model that basically Bailey first introduced in 1954, right. So, here the server can process partial batches up to a maximum size of k. As before, the customers are served k at a time. If there are more than k customers, it will take the first k customers or whatever order in which the customers are chosen, k customers are chosen, and then the service will start. Okay. But if there are less than k customers, right, the server will begin service on those less than k customers, right. Further, what we are assuming is that when there are less than k customers in service and the new arrivals that might come during the service period of these less than k customers who are currently being serviced, right, they can immediately join the service up to the limit of k and finish with everyone else regardless of their entry time into the service. Okay. And the service times, as earlier, is for batch, whether it is a batch of size k or less than k, and anyone who joins in between when in an ongoing service, when the server is not full to its full capacity, they will all finish together and the service times are exponentially distributed with parameter mu. This could be, for example, in a guided tour, right, or some explanation, some puppet or movie show, right. Suppose if you are looking at some show, the show will begin as long as some customers are there. Possibly here we can generalize, any number of customers is there, the show will start. Now, anyone who arrives late will simply join the show and the show will finish for everyone at the same time, right. A movie show, a light and laser and light show, this kind of shows, like you can think, or a guided tour. For example, you are going to some tourist place and the guide explains the significance. The guide will start with some number of customers and then as people come, they will join in the intermediate and then they will finish with everyone else at the same time, right. Of course, I mean, even in a real life situation, you can think about many such situations where this partial batch model would hold good. Okay. So, we will consider these two variations of such a single server Markovian queue with bulk service. Okay. But there are many other variants with respect to this bulk service. I mean, that's the beauty of such queuing models. As you would see, when you observe, you would find that this doesn't really fit into any of the existing models that you have in your hand for analysis. So, what do? You create a new model. It's always, as always, you do that. And there are other variants. The prominent one is what is called the general bulk service rule, or many a time it is simply referred to as GBS rule, which was basically initiated in 67 by Newts, and in which the service is rendered with a minimum batch size of L and with a maximum batch size of K, right. So, you have the K like in the previous description, the previous service rules that we have followed, but suppose if you think in a partial service, partial batch model, it will start with any number of customers, even if there is one, but it may not be economical to start with one. So, you want it to reach to at least to some level, say L, that is what this would mean. But there is a difference between that, we will come to that. Okay. So, what is how it is being operated? If there are fewer than L customers in the system at the time of service completion of a particular batch, then the server will remain idle until there are L customers, and when as soon as it reaches the L customer, it will start service for this L customers. And if there are L or more at the time of service completion epoch of a previous batch, but then less than k customers are waiting, then all of them are served together. If there are more than k customers waiting, then a group of k enters into service according to the policy that you have. So, the corresponding model, this model is typically denoted by MMLK/1, or more common it will be something like m a comma b slash 1, this is same as this, okay. So, this is the same as this, because I am just writing, because this is the notation that you might find in many books. So, that is the model that you have, which is what a general bulk service rule. A and B are the levels. Since we have already have K here, so we just defined another one L to denote it in this manner. It is the same, there is nothing on that. So, this is just a notation, whichever these are the same, okay. So, examples include this airport shuttle, right. So, when you are trying to board in the shuttle, like at least some number of customer come, then it will start. It may not be full, the bus may not be full when you are getting into the flight, right. So, or a lift in a building ground floor, probably it is being operated by a person. So, even just one person entering, he may not start the lift. So, he wants, may not be full, but at least some number of customers come in, so that he will start the lift. Suppose if it is a big story, right, some 40-50 floors of building, and then you will not be able to operate for every one customer, right. So, you will want, you may wait for some time until some more customers join in, right. So, that is the lift, or a traffic flow, which is basically described in this newspaper itself, like where a minor road merges into a major road. So, there is a major road and there is a minor road which comes and merges with this. So, the traffic coming from that minor road, when it will be let inside the major road, blocking the traffic of the major road, right. Since this is the major road, you will not block until there are at least L number of cars or vehicles that are coming in the minor road, at which point then the traffic is stopped in the major road, and this is minimum L has to be there, or sometime that is what you would look at. So, that is the another example, or many other examples also you can think. But now, the difference between previous model and this model is basically what we are describing it here. The difference may be there, may not be there, depending upon how you are pitching it. What is that? Systems where the customers can join or access an ongoing service batch any time before the service of the batch is completed, provided the specified maximum service batch is not reached, are known as systems with, this is the word that is used, accessible batch service. Okay. So, the previous one, that partial batch model that we have considered, is basically a system with accessible batch service, right. Whereas, in this particular case, for example, lift, suppose if you are thinking, right, lift if you are thinking, of course, once it starts from the ground floor, then even with less than the full capacity, then the arriving customers on the ground floor cannot access. So, the service that is being provided to the already existing customers, right. So, in that case, it is basically a non-accessible batch service system, right. Whereas, in a traffic flow, depending upon how you operate, right, you can think that at the point of start of the service, whatever vehicles is there, only that will be allowed to go into that. Anything that is coming after that, we have to wait for the next cycle, then it is non-accessible. But during the course, suppose if some more vehicle comes and you also allow that to pass up to a maximum of k, that k is there, up to a maximum of k, then it become accessible. So, like that you can think about the models which are variants of this, right. Whatever it is, this is the feature. Now, the literature on both accessible batch service model and non-accessible batch service models are plenty. There are different situations that require the model to be studied in both the scenarios, under both the scenarios, right. So, if it is accessible, then both the previous two models can be thought about as this general bulk service rule. But if it is non-accessible batch service model, then at least the partial batch would not be, you would not think about this part, a special case of this, but the fixed size you can always think about it, right, as this, where L equals k is what then will give you the fixed size one, right. Another variant could be that the size of the batch being the random variable, depending upon the unfilled capacity of the server, right, up to a maximum of k. When the remaining one you can send in that the random, again you will not send all, but you may send a partial one, that could be random. Again, this is all studied, but we consider here only the previous 2 models. So, these are all some idea about what could be the general models that one can think along those line that we are going to discuss. Within the Markovian framework itself, like you can think about different service policies will give rise to different models. Now, what is the the kind of policies that you can think of? Of course, it will be depend on the system, and accordingly you can develop. So, that is why to give a hint that we are mentioning this, but we will be considering only these models like MK1 full batch model and partial batch model, and partial batch model with this notion of accessible batch service is basically we are looking at the partial batch model with accessible batch service, not with non-accessible batch service models, right. So, these are the 2 models that we are going to consider next. Okay, that's the our objective in this session, right. So, what is the first model is that MK1 partial batch model. Every assumptions we have already described, it is a partial batch model. So, the underlying model is a continuous time Markov chain which we are describing through this particular transition rate diagram. Look at state 0. In state 0, when it will be there, right, it will move to state 1 when there are 0 customers there, or it will move to state 1 with rate lambda with an arrival, and immediately its service can start, right. It is because this is a partial batch model. So, the moment there is one customer, the current service will start. So, it can go to 0 again with the rate mu, or from 1 an arrival can happen, it can, so our service is already started, right, for this already one customer who is currently in service. Now, if another arrival comes, the system will move to state 2, but now both will be there in service, and with rate mu their service might end and the system will reach to state 0. Clear? The same thing from 2 to 3, and from 3, because already 2 is in service, one more arrival happens because this is accessible batch service, partial batch model. So, the service is happening for these 2, another one joins, service will start for all 3, service will continue for all 3. And if the service completion happens before the next arrival, then the system will move to state 0, right, which can happen. This similar kind of behavior can happen up to the state k in a similar fashion, right. Or when it is in k minus 1, an arrival can make it to k, and at which stage this can all the k will finish the service. If they finish the service together before the next arrival, then the system state will move to state 0, right. And one in k, if it moves to k plus 1, right, now actually the only k are getting served, because the one customer that will come at this point of time, he will not get into the service immediately, whereas up to this point any arrival in any of these states will get into the service immediately and finish with others, whereas from k onwards any arrival that comes into the system, he will really be in queue, right. The one customer will be there in the queue, already for k customers the service is going on. Now, from k plus 1, then when the service completion happens at this rate mu, the system will move to state 1, right, and from k plus 2, right, when the service completion happens with the rate mu, the system will move to state 2, and so on it will happen. So, from this point onwards you will have a uniform behavior for each of these states, right. Up to this these things will behave slightly differently because of this partial batch thing. From all of these states the system state will reach to 0 at the service completion, and from here onwards, right, the system will reach to n minus k is what then will happen, right. So, that is precisely, so then if you write the balance equation, now if I write for the state 0, right, from 0 there is only lambda, with the rate lambda I can move out of the state 0. So, lambda p naught on the one side, but I can reach state 0 from state 1 with the rate of mu, from state 2 at the rate mu, from state 3 at the rate mu, from the state k minus 1 at the rate mu, and also from the state k at the rate mu, and beyond that there is nothing, there is no other way I can reach state 0. So, mu p1, mu p2, mu pk minus 1 and mu pk is what then would be the total, the flow into the state 0. So, this one is for the state 0, flow out of state 0, flow into the state 0 is what you are writing it here, right. Now, for all other states, if I look at here, right, for all other states, the flow out of this particular state is basically either an arrival can happen or a service completion can happen. An arrival can happen or a service completion, arrival or service completion, arrival or service completion, arrival or service completion with the corresponding rates lambda plus mu. So, this is the flow out of the state n for all n greater than or equal to 1. Now, similarly into this, right, from the previous state with one arrival I can reach here, or with the service completion of n plus kth one, if I am looking at the nth state, then n plus kth from state, a service completion will bring it to state 1. That is with the rate mu n plus k, mu p n plus k from the state and lambda from the state p n minus 1, right. So, this is then the balance equation for the general states where 1 to infinity, right, clear. So, this is what is the partial batch model, right. Now, we have described the partial batch model and we have written down now the flow balance equations or the global balance equations for this particular system, right. Now, what we have to do, we have to solve this system in a usual, as per our usual process. Once we written down, then we have to solve. This is the steady state balance equations, right. Now, we look at the general equation, we will come back to this equation in a moment, but we look at now the general equation, right. We can solve by generating by function method or other methods, but we will use the operator method here, right. So, the general equation can be written in the operator notation as mu times p n plus k minus lambda plus mu times p n plus lambda times p n minus 1. Right. So, this is what I can write it for n greater than or equal to 0. So, n minus 1 I have made it as n greater n minus 1 with n greater than or equal to 1 is same as n with greater than or equal to 0. So, the equation in the operator notation using the d is, we can write it in this form, right. Now, if I have to use the operator method, then I have to write the characteristic equation which will be equal to some mu times r to the power k plus 1 minus lambda plus mu times r plus lambda, and I am going to look for roots or zeros of this polynomial or these roots of this characteristic equation, and so there will be, this is a polynomial of order k plus 1. So, there will be k plus 1 roots are there. So, some k plus 1 roots are there for this operator or the characteristic equation, then we can write in terms of those roots this Pn as in this form as a solution in the usual way. Now, this condition, the usual condition of total probability being equal to 1 implies that in order that this be bounded, that summation Pn is convergent, then Ri must be less than 1, or if Ri is not, the roots are not less than 1, then the corresponding Ci must be equal to 0. We have seen it in MM1 case exactly similar argument, the same argument here also, right. Now, we have to know how many roots of this, out of this R1 to Rk plus 1 are less than 1 and the condition, for which we appeal to Roche's theorem. As I said that even in steady state analysis, we will use the Roche's theorem idea, right. Here is one such example, that by appealing to Roche's theorem, it can be found that there is exactly one root which we call it this R naught. So, out of this R1, R2, Rk minus 1, there is one root which is strictly less than 1, that is in the open interval 0, 1. That root we are calling it as R naught. So, one of this R1 to Rk plus 1 only we are calling it as R naught, and this will be under the condition for the stability of the system. So, which is basically lambda by mu would be less than k is what, or lambda by k mu is less than 1, which is what is typically denoted as rho. Now, you can look at this, how one can show this, like by looking at this auxiliary equation, you want to show that there is exactly one root under this condition. Now, like this, you can take G to be this and F to be this and apply the Rauch's theorem on the unit circle, that you will be able to see that there is exactly one root which will be strictly less than 1, and that root will be real and it will be strictly less than 1 provided this condition is true. Okay. Now, this implies then that, so for all other roots then Ci is equal to 0. So, for this root there will be some constant C will be there. So, that C times R naught to the power n would be the solution for n greater than or equal to 0 and for R naught less than 1, strictly between 0 and 1, and this total probability equal to 1 will give me my C as 1 minus R naught. So, the total steady state distribution for this partial batch bulk service model with accessible batch service is basically a geometric distribution which looks much like your MM1 model, but the rho is now replaced by this root of this characteristic equation, which is the single root which is less than 1 is what is taken to be this R naught. In terms of that, you have this. Otherwise, the look, the form is similar, but basically the R naught takes the role of rho. Now, once you observe this, then you can write down the performance metrics similar in a similar way in the usual manner, but we can always make an analogy with MM1 and we get L as this and W as L over lambda, because this is rho by 1 minus rho. So, here R naught is what is taking the role of rho. So, W is L by lambda. So, that means this quantity, and using Little's law again WQ is W minus 1 by mu and LQ is L minus lambda by mu. Alternatively, one can directly compute from the steady state probabilities that LQ is equal to R naught to the power k times L, which is equal to LQ L minus lambda by mu. These are all exercise in your book, but of course, you can try. It is not a very complex ones that you have to try if you want to understand the theory better. Okay. Now, let us look at a simple typical example, which is a self-service car wash facility. Suppose they want to install a new machinery that permits the washing of 2 cars at once, and if one car, if there is no other car is there. So, either one car it can serve or 2 car it can serve, and whenever a car that arrives when while a single car is being washed joins the wash and finishes with the first car. May not be such a realistic one, but it can happen and you assume, otherwise you can cook up another example where this might hold. But anyway, we are just to illustrate in this particular case, and there is no waiting capacity limitation, which means any number of car can wait. Cars arrive according to a Poisson process with a mean of 15 per hour. Time to wash a car is exponentially distributed with a mean of 6 minutes. So, the data given is that lambda equal to 15 per hour, mu since it takes 6 minutes it is 10 per hour, and k is equal to 2. So, you can see here that rho, which is lambda by k mu, so it is 15 by 20, it is less than 1. So, the characteristic equation will have a real root which is strictly less than 1, stability of the system is guaranteed. So, the characteristic equation then would be equal to this, which can be written in this form. Okay. You can always see that this particular characteristic equation, right, 1 is always a root, right. If I put d is equal to 1, then this is identically equal to 0. So, 1 is always a root. So, observing that one root is 1, so then this reduces to this equation, right. If you divide by the r, you can write it as r minus 1 times this, you will get this expression, right. So, this gives me my r as these two values. Now, from this there are two roots, the one that will be within less than 1 is this r naught, which we obtain it with a plus sign here, is this root, So, now once I obtain this, now I know what is the distribution of the number of customers in the system. Pn's I can write in terms of this R naught. I can compute L, because that is the interest in this particular case. We want to see how many cars will be waiting if this is the system that is being operational, and how many will be there in the system and how many would be there in the queue. So, we are observing that 4.6 number of cars will be there in the system, and 3.1 car will be waiting at on an average at any given point of time in such a system. Then you can decide whether this is sufficient, or you have to do something more to either increase the rate, so that if this you feel this is unreasonable, then you have to reduce. If you want to reduce, then you can do all those things, right. That's a typical example where you can use this kind of analysis, right. This is the partial batch model. Next, what we will consider is the same, but with now full batch model. So, what is the difference is that now the batch size must be exactly k for the server to start the service, right. If not, the server will wait until such time to start. So, now if I go back to the diagram and see like what would be the difference in that scenario, right. When there is a 0, arrival can bring it to 1, but now with 1 service cannot start because of the full batch model. So, he will not get into the service. So, and hence there is no possibility of moving from state 1 to state 0 with rate mu, because service is not happening. So, this magenta line from 1 to 0 would not be existing. Similarly, when it is in 1, since service is not being done for this one customer already in the service, only can arrival can happen in this situation, which can bring the system to state 2. Now, from this system 2, since again the service is not happening, so there is no possibility of movement to state 0. Again this magenta line or magenta arrow, this transition would not be existing. It can only move to 3 and so on all the way up to k minus 1, and again from k minus 1, since all this k minus 1 customer will be waiting in the queue, they will not be getting served. So, again there is no this magenta transition line that we are putting in this graph. So, it can only move to k. At this point of time, service will start for this k number of customers, and from here it can make either move to k plus 1 or it can go to state 0. So, from this point onwards, if I look at the transitions would remain the same. So, this equation would hold now for all n greater than or equal to k, right. But for these states 0, 1, 2 up to k minus 1, it will have a different set of equations which is different from this for the state 0 as well as for all the states between 1 to k minus 1, you are going to have a different set of equations, and that is precisely this, right. So, from 0 can be reached only from state k with the service completion. Similarly, for anything 1 between 1 to k minus 1, this the move out is only lambda times Pn, but it can be reached from n plus k to n or n minus 1 to n. These are the only rates, that we have seen that. So, this is the difference. This equation for all the states n greater than or equal to k remains the same whether it is full batch or partial batch model, right. Full batch or partial batch model, that is what would happen now, right. Now, so this equation, since it is identical to that of the partial batch model, and hence taking this equation, proceeding in a similar way as we have done for the partial batch model, meaning write down the this equation using in operator notation, taking the characteristic equation, looking at the roots, finding out there is only one root which is R naught. We can write Pn as C times R naught, but now this n is true for all n greater than or equal to k minus 1 only. There we have written n greater than or equal to 0, but here it will be written for n it will be true only for n greater than or equal to k minus 1, for 0 less than or not less than 1. Up to this the process is the same, but now we have to obtain C, and using that P naught but now this is a bit complicated here. That is the difference between that. Up to this part you will do as you are done for the partial batch model. Now, what one can observe from the first equation, I can write Pk to be lambda by mu times P naught, right, but from here Pk is C times R naught to the power k. So, that gives me what is my C in terms of P naught first. Okay. So, by plugging this C into this expression, I will get Pn to be P naught times lambda times R naught to the power n minus k by mu for n greater than or equal to n k minus 1. So, I have expressed Pn in the first step in terms of P naught. That is what we have done here, right. So, this is one part we have done. Now, I have to look at other Pn's in this range 1 to k minus 1. I will try to express in terms of P naught. Then I can utilize the total probability equal to 1 condition to obtain this P naught. That is the idea. So, basically now I have not yet used this equation so far, the middle set of equations, and this set of equations is what we are going to use this k minus 1 equations, and if I write this k minus equation in this fashion, that mu times P n plus k is equal to lambda times P n minus lambda times P n minus 1. Right. So, I can iterate this, or using the geometric form of Pn for n greater than or equal to k minus 1, right, and substituting for P, because this Pn plus k I already defined what is that, right. It is in terms of P naught whatever this expression that we have written down here, right. And then this one if I do, right, if I do that, then you will be ending up with this expression, right. You will be ending up with this equation, right. You just substitute for this, we will end up with this equation. So, Pn minus Pn minus 1 is P naught times R to the power n. Now, this equation can be solved iteratively starting with n is equal to 1, or alternatively what we can observe is that these are again linear difference equation, but is non-homogeneous linear difference equation whose solutions are again in this form for C1 and C2 R naught to the power n, right. But direct substitution into the above equation, right, Pn I substitute into this equation will give me C2 as this, right, and the boundary condition at n is equal to 0 would give me C1 as P naught minus C2. So, if I substitute these together into this Pn, so C2 is, I have already described it in terms of this, C1 is again in terms of C2, but C2 is again in terms of this. So, substituting all of this, what you would get is this expression, which you can easily verify, right. So, now I have Pn's which I have already determined for n greater than or equal to k minus 1 in terms of P naught, which is what this expression. Now, using this k minus 1 equations, my Pn for these n's I have described in terms of P naught here, right, Pn's. Now, all the Pn's now I have expressed in terms of P naught. Now, I can use this total probability 1 condition to determine P naught using this boundary condition. If I do that, then I will be getting this expression, right, simply, but this is a geometric expression which will give you this, and this one, the first term will give you this, the second term will give you this expression, the finite sum with respect to this R naught is what then will give me this one. Now, again you simplify by taking the LCM, like you take this common and then you get this equation. But now you observe that R naught is the root of the characteristic equation. That characteristic equation is precisely this component, right. So, that tells me that R naught satisfies that, that means this quantity is 0, right, this quantity is 0. Now, if I substitute that here and then 1 minus rho naught will go away, and so this is what you will get, and which is equal to then 1 minus R naught by k. So, now P naught I have determined, as 1 minus R naught by k. Pn I have determined in terms of this P naught. So, I have now determined completely the steady state distribution for this full batch bulk service model. Now, in the other performance measures of interest, whatever if you want, you can obtain it in terms of from this distribution, right. So, that is always possible. Okay. Alternatively, this can also be obtained through generating function approach, which of course, we will not do, but of course, we have seen that this is the solution that you can get for this model, right. So, this is full batch model. Now, you can use this models itself, like suppose if you have to use non-accessible batch service, how you can modify. It can happen only in the partial batch case. So, if it is non-accessible case, then what one has to do is that for all these states, you need to have a parallel state where whether service system is not empty, but whether someone is waiting or no one is waiting, means the system is busy serving someone or without serving someone, server is wait. So, that kind of expansion will happen in terms of the states of the process. From here onwards, of course, things will remain the same and so on that you have to do. So, you have to make modification, you can see how one can do. So, for simple case of say 2 or something, if you put, then you need to introduce only one more state and then you can analyze that model easily, right. So, these kind of variations one can do within this idea. So, this is all about the MK1 partial batch model and full batch model that we have seen. Okay. So, again as we said, there are many different service rules and accordingly the model can be analyzed under such scenarios as well, but things are complicated, we are not getting into that. For us, this is sufficient that we get an idea about how one can handle the general the bulk service models using these two models. Okay, so, with this we conclude the discussion on this bulk queues here. Thank you.